Thanks for the introduction. So I'll begin by just telling a story about Gopal. So the experience of working with him on this material is, certainly was one of the most rewarding experiences I had in my work in mathematics. And I learned a lot about both things mathematical and non-mathematical. And so I'd like to just mention one of the non-mathematical things I got out of it, which was appreciating the value of hard deadlines to make sure things really get done on time. And so in the process of writing this book, which I'll say something about in a little bit, we decided we were going to dedicate it to Jacques Tits, and Gopal said, let's dedicate it to him for his 80th birthday. And that was a great decision, because 80th birthdays only happen once, and they can't be pushed back. So that deadline certainly forced a lot of focus and made sure that we got everything done on time, as we did. Okay, so this topic that I'm going to talk about of pseudo-reductive groups has several different references that I'll be referring to during the presentation. So the main book, which is this one, which was written with also with Ofer Gaber, where we kind of lay out the general theory. So this is a kind of pretty thorough reference. There was a later book that we wrote called Classification of Pseudo-Reductive Groups that developed some refined aspects that I'll get to towards the end of the talk that was written with Gopal. And this included some simplifications to the general theory developed in the big book. And we wrote Gopal and I wrote a general survey article on this called Structure and Classification of Pseudo-Reductive Groups, which is if you want to sort of get a sense of the overall theory, taking advantage of the simplifications from the second book, but giving a kind of overview, including the material of the first book, this survey article is probably a good place to begin. And one of the main reasons that we actually did all this work was to give the input needed to push through certain proofs of new finiteness results for general, possibly non-reductive algebraic groups over local and global function fields. And so that was a compositio paper that I wrote. So I'll say a little bit, I'll refer to that a little bit in the main presentation. Okay, so before I get to the definition of what a pseudo-reductive group is, I'd like to first give some motivation. And so the basic task that I want to sort of have in mind at this point is that sometimes one is confronted, and I'll give some examples in a moment, sometimes one is confronted with questions involving a linear algebraic group over a field about which one has very little information. And the group might not be reductive, and if the ground field is not perfect, then reducing the problem to the reductive case can often seem basically intractable. And so that's the thing that we're going to try to overcome. So let me give some sample questions involving fairly general algebraic groups. Oh, and I should say that the kinds of imperfect fields that one might have in mind would be things like local and global function fields, or more generally, function fields of positive dimensional smooth varieties, perhaps even over an algebraically closed field of constants. Okay, so here are a couple of sample situations. So the first example, and these were some questions that were considered by Borel and Tits, and they, as we discovered later after we began this work, Borel and Tits had actually introduced this notion of pseudo-reductive group, and they did a little bit with it, but they weren't able to get as far as they wanted. And so here are some of the questions they were kind of wondering about. So suppose you let G be just a connected linear algebraic group over a field K. So this is a smooth affine group, and for what I'm about to say, the interesting case will be imperfect K. And then you could ask, for instance, for a split maximal, for maximal split, K torite S and G, are they all GK conjugate to each other? Okay, certainly in the reductive case, that's an important and well-known fact, but does it hold without assuming reductivity? And you can also ask the same for maximal split unipotent smooth connected subgroups, U, inside G. Right? So in the reductive case, these would be the unipotent radicals of the minimal parabolic subgroups. But in general, what can you say about these? Do they constitute a single rational conjugacy class or not? And finally, third question that they kind of wondered about was, does G of K admit a structure of a TIT system? Okay. And again, for a reductive group, one makes TIT systems by using maximum split tori and minimal parabolics. But for a fairly general G, what can you say? Is there some mechanism, some way to get a handle on G of K to sort of show that it admits a TIT system? Okay, so that's one class of questions. But you might feel like, well, okay, these are about general G because, well, you started with a general G. So the fact that you're confronted with general G is kind of put in by design. So it's really a question of just, can you generalize certain properties beyond the reductive case? But let me give another example, which starts with perhaps a reductive group, but quickly leads one to a linear algebraic group about which one knows almost nothing. So let's suppose we have the following situation. So X might be a maybe a quasi-projective variety, if you like, over a global field. And for what I'm about to say, the global function fields would be the most interesting case. But anyway, and this is just an affine algebraic K-group scheme. So it could be a smooth affine group, for example, even a reductive group, even GLN. Right? And what we want to think about is how can we tell whether two rational points of X are on the same G of K orbit or not? Can we check this locally? Okay. So if I give you a point X naught in X of K, let me introduce the set that I'll call so sigma X naught. So what I'm going to think about is all the points in X of K, which lie in the same local orbit as X naught for all places, and consider this set of points up to the global action by G of K. All right? And the question you want to ask is this finite? Okay, so is it the case that the gulf between being in the same global orbit and being in the same local orbits at all places is that gap? Oh, I'm sorry. I left off a very important hypothesis. Well, anyway, you could ask this question, but the thing we want to assume to make this interesting is we're going to assume that GK bar acting on XK bar is transitive. So geometrically, we'll assume that the action is transitive, and again, maybe we even want to focus on the case where G is let's say G is a smooth group scheme. So let's say it's smooth. Okay, so anyway, so that's the question. Is the gulf between global orbit and everywhere local orbit actually finite or not in this kind of geometrically transitive circumstance? So to analyze this, let's introduce a certain torsor. So I give you some X, it's a rational point. Let me let E sub X, well, functorially, it's going to be the points of the group which carry X to X naught. Okay? This is non-empty because the transitivity hypothesis, this has a geometric point. And so this is easily seen to be a right torsor for the stabilizer. Actually, let's go the points that carry X naught to X. So this is easily seen to be a right. Well, if I multiply G on the right by something that stabilizes X naught, it's still in this functor. So this is a right torsor for GX naught. So the scheme theoretic stabilizer of X naught. Okay. And so so one can show that by associating to each point this torsor, you actually get an injection of this coset space mod the global action into the degree 1 Tate-Shafarevich for the stabilizer scheme at x naught, where you associate to each point this torsor. So if the torsors are isomorphic as torsors, then you can show the points are in the same global orbit. Okay? And so this set that we don't know much about injects into this degree 1 Tate-Shafarevich for this group scheme, let's say using the FPPF topology in case this is not smooth. And by a small trick that I won't get into, one can show this is the same as the Tate-Shafarevich for the maximal smooth subgroup. Okay? This is not the underlying reduced group scheme. Okay, this is the maximal smooth subgroup. It's essentially the Zariski closure of the set of separable points. Okay? And the thing I want to stress is that one's not, of course, if K, and particularly if K is not perfect, right, the maximal smooth and the reduced subgroup are really can be quite different from each other. In any event, the point I want to stress is this maximal smooth subgroup is a complete mystery. Okay, even if G is like GLN, God only knows about this thing. It can be highly disconnected, and this identity component, we know nothing about it. Okay, so if you want to answer this question in the affirmative, you would like to have a finiteness result for Tate-Shafarevich of quite general smooth affine groups over global fields, particularly global function fields. Okay, and yeah, so the answers to both of these questions in these examples, so the answers are all affirmative. And the question is, what mechanism do you use to deal with this? And so I just want to kind of say the informal principle, which is that the structure theory of pseudo-reductive groups, so I have to define what that concept is. This is a certain generalization of reductivity, which is the same as reductivity, connected reductive, over perfect fields, but over imperfect fields, it's a more general concept. And these will have a very rich structure theory, as I'll be discussing. And so the structure theory of pseudo-reductive groups often allows one to reduce problems for general smooth affine groups over a field to the cases of commutative groups over K and connected semi-simple groups over finite extensions. Okay. Now, the thing I want to say, I'll give some indications about this, but the thing I want to emphasize is that when you're working over an imperfect field, it's not, over a perfect field, it's very easy to reduce many questions about a general linear algebraic group to the connected reductive case. Okay? For reasons we'll get to. But over imperfect fields, is basically, there's no easy way of doing that. And the point of the structure theory of pseudo-reductive groups is to basically allow you to kind of do the impossible, meaning to actually push through such things, but at the cost of having to work over finite extensions. Okay? But the thing I want to sort of highlight before we get into this is there's not some kind of meta theorem that just says, oh, there's this one universal recipe to always do this, but rather it's the nature of the structure theory that allows one to often push through such things. But depending upon the particular application, how you use the structure theory to kind of implement this principle in a specific situation can vary from situation to situation. And so if you look in this paper that I wrote on finiteness theorems, which uses all of this stuff, you'll see a wide variety of different kinds of situations where one uses the structure theory in a variety of different ways. Okay? But that's kind of the goal of the whole thing. We want to set up a kind of structure theory beyond the reductive case, whose formulation somehow makes it possible to reduce general problems to separately considering the commutative smooth connected case and the connected over the ground field, and the connected semi-simple case over finite extensions, which may be inseparable extensions. Okay, so great. So let me, just to get started, so that's kind of just the warm-up motivation for the kind of things that we would like to be able to do with the theory that I'll kind of give a kind of brief outline of in this sort of talk. Oh, and maybe before I start giving some definitions to give this some solid footing, I should sort of stress that this is not a kind of geometric theory. Okay, so whatever this notion of pseudo-reductivity is and the way that it's used, everything is very sensitive to what ground field you're working over. So this is kind of one reason that this stuff was sort of not discovered or developed back in the 1960s, because it's very sensitive to the ground field. So there's not like a version of this over rings and so on. Okay. All right. So so let's into some sort of basic definitions and facts. Okay. And so let's start with some definitions. So suppose G is a sort of smooth affine group over a field K. And I'm going to define R sub U K of G. I'm going to call this the K unipotent radical. And this is going to be the maximal normal unipotent smooth connected K sub G. Okay? And so we call this the K unipotent radical. And then we have the what we'll call the K radical, which would be the maximal normal solvable smooth connected K sub. Okay? So these are just some definitions. And one thing that's pretty easy to see is if I give you an extension, capital K of little k, and you consider the unipotent radical, the K unipotent radical over little k, and you extend the ground field on it, then it's certainly contained in the capital K unipotent radical of the group over capital K. And likewise with the K radical, with the little k radical. Okay? And these are equalities if capital K over little k is a separable extension. Not necessarily algebraic, like this could be the completion of a global field. Okay? So these subgroups are just kind of abstract things. They're well behaved under separable field extension, but in general, those are usually not equalities. So these containments are usually not equalities if K over K is not separable. Okay, and the main case of interest would be this is the algebraic closure of an imperfect field. Okay, so let me just give you some examples. So especially, so if K is not perfect, then it often happens that if you take the K unipotent radical of a group G and you look at it geometrically, this is actually strictly smaller than the unipotent radical of the group over the algebraic closure. Okay? In fact, we're going to see there are many situations where the K unipotent radical is trivial, but the geometric unipotent radical is non-trivial. Okay, so these can really be quite different from each other. Okay, and so a kind of very basic class of examples, and this is discussed. This is in the CGP book. This is example 1611. So if K prime over K is a purely inseparable non-trivial finite extension, and G prime is a connected reductive K prime group that's non-trivial, then, so we start with a kind of non-trivial connected reductive group over a non-trivial purely inseparable finite extension. And then what we do is we sort of try to turn that into a group over the ground field. So I'm going to write this in the following informal way. I'm going to take G of K prime viewed as a K group. Okay? This will be made rigorous via the notion of Weil restriction of scalars from K prime to K a little bit later. But roughly speaking, the idea is that you take K prime and you write it in terms of K using a K basis. And then all the equations defining K prime, you write them over K in terms of this choice of basis. So this G of K prime, roughly speaking, becomes like a group over K, somewhat in the same way that a complex Lie group can be viewed as a real Lie group with twice the dimension. In any event, when you do this, oops, that's a G prime there. But when you do this, this turns out to satisfy that its K unipotent radical is trivial, but geometrically over K bar, the unipotent radical is always non-trivial. And this is ultimately due to the fact that K prime tensor K, K bar has nilpotent elements that are non-zero. Okay, precisely because K prime over K is a non-trivial, purely inseparable finite extension. Okay, so these non-trivial nilpotents geometrically turn out to give rise to this sort of non-trivial geometric unipotent radical, but this group itself, its K unipotent radical, is actually trivial. Okay, so we'll come back to this a little bit later, but at least, so this is, of course, a huge source of examples where this non-equality happens. In any event, it leads us to a definition, which is, we'll say, so in this generality here, so we'll say that a smooth connected affine group K group G is pseudo-reductive if its K unipotent radical is trivial. And we'll say that it's pseudo-semi-simple if it's pseudo-reductive and perfect. Okay? And it turns out this implies that the K radical is trivial, but the converse is false. Okay? So there are examples of K groups whose K radical is trivial. In particular, they're pseudo-reductive, but they are not themselves perfect. So an example of this, in this context here, K prime over K, non-trivial, purely inseparable finite extension. So roughly speaking, if you take PGLP of K prime viewed as a K group, I mean, this is made rigorous using the Theta restriction of scalars, as we'll discuss later, then this is an example of such a thing. This turns out, as a K group, not to be perfect. It has a kind of determinate map to K prime star mod K star, because K, well, really I should guess here, oh, sorry. So if I'm going to do this here, maybe for PGLP, I should be taking, let's say, K prime over K to be purely inseparable with degree P. Okay? So in any event, this is an example of such a thing. So this is not the thing that gives the right definition. We just sort of impose perfectness by hand. Okay, so anyway, so these are just basic definitions. And so we're going to see these have a very, very nice structure theory. But before we get into it, I just want to tell you some bad news. So give you a few illustrations of ways in which this notion of pseudo-reductive and pseudo-semi-simple have some features that are a little bit disorienting relative to what one is used to from the reductive and semi-simple cases. So let me start with the bad news, some bad news. So first of all, the commutative reductive groups, commutative connected reductive groups. Oh, and I should say, of course, when K is a perfect field, right? These are exactly the familiar notions of reductive and semi-simple. Okay? But over imperfect fields, these are much more general concepts. But a general G is very easily related to this case simply by quotienting by its K unipotent radical. Okay? So these naturally show up in the study of a kind of general G over a general K in the way that a reductive group would not. Okay, so what are some delicate points that one has to be careful about? So first of all, the commutative connected reductive groups, those are tori, right? And those we can kind of get our hands on because they're Galois lattices. Okay? But in the commutative pseudo-reductive case, it's a complete mystery, right? So commutative pseudo-reductive groups are a kind of, you should be regarded as a total mystery. Okay, they're very hard to describe. There's no, I mean, over imperfect fields, okay? And so just for example, so in CGP example 163, just to show you how different these are from tori, for every imperfect K, there's a commutative pseudo-reductive K group C for which the group of separable points has non-trivial p torsion, where p is the characteristic. Of course, this never happens for tori, and it never happens for Weil restrictions of tori. Okay, but anyway, so the structure of these things is really quite baffling. Also, another thing you have to be careful about has to do with quotients. Okay, so this is CGP example 164, which is that again for any imperfect k, there exists pseudo-semi-simple k groups G and pseudo-semi-simple normal n inside of G, which the quotient G by n is not pseudo-reductive. Okay? So again, that's very different, right? For reductive groups, quotients of reductives are always reductive, but even a pseudo-semi-simple group, so it's not kind of being interfered with by the commutative case because it's perfect, a pseudo-semi-simple guy can actually have a non-pseudo-reductive quotient modulo the pseudo-semi-simple normal subgroup. Okay, so that's kind of disorienting. And likewise, there even exists central quotients. Which are not pseudo-reductive. Okay, so this is, again, all quite disturbing relative to one's kind of familiar experience. All right, so the behavior under quotients can be kind of problematic. And you can also make other problematic example situations where like Z mod P, the constant group Z mod P is in the center. Okay, and so again, that you sort of never really see in the reductive case. Okay, so having told you some bad news, just to emphasize, you have to be a little careful about these things. Let me tell you some good news. Okay, so first of all, to get the good news off the ground, we need to get started. So the structure theory starts with the following. So I'll call this the magic lemma. Okay, and I just want to sort of say, I mean, getting the whole structure theory off the ground will take a lot of work. And in fact, the reductive case over the algebraic closure is going to be a key ingredient in proving many things. But I want to give just one proof in this presentation. I'm going to discuss this, this magic lemma. And this is going to be a tool that allows you to use the pseudo-reductivity hypothesis to get conclusions using information from the geometric fiber over K bar. Okay, so it's the following statement. So say G is a pseudo-reductive group, and X inside of G is a geometrically integral closed subvariety, which contains 1. Okay? And the statement is that if X over K bar is actually contained in the geometric uniform radical, then X is actually equal. Okay, so that's the so it's a tool for using pseudo-reductivity to show that certain kinds of closed subvarieties are necessarily trivial, everything here over K. And the proof is quite simple. The observation is, well, roughly speaking, let me take all conjugates of X by points in G over the separable closure, and take the subgroup generated by all of these conjugates. These are all a whole bunch of subvarieties that pass through 1. And so this is stable under the Galois group. So it descends. So this is a smooth, connected, normal K subgroup of G, right? Because of how it's built. Great, because you do all these conjugations, so it's normal. But by design, X over K bar, right, by hypothesis is inside the uniform radical geometrically, so all these conjugates are. So H over K bar is contained inside the uniform radical over K bar. So actually, H is unipotent. But being a smooth connected normal K subgroup, we get that H therefore is inside the K unipotent radical, which is trivial precisely because of the pseudo-reductivity hypothesis. and therefore, since H is trivial, obviously X is also trivial. Okay, so this is called magic lemma, and yeah, and so this has a bunch of nice consequences. So I'm going to tell you a theorem, which is like the first, real theorem that kind of just largely builds on the magic lemma, but it also uses a few other ingredients I won't go into. But just it'll reassure us that despite these bad features, pseudo-reductive groups do have some properties that are kind of reminiscent of what we know from the reductive case. So let G be a pseudo-reductive group over a field. So then, first of all, if it's solvable, then it's commutative. Right, so that's good, right? Just like in the reductive case. Also, its derived group is its own derived group, right? So its commutator subgroup is perfect, just like in the reductive case. And two other nice properties that will involve torus centralizers. Okay. So we have a K-torus inside of G. So if S in G is a K-torus, then its centralizer is again pseudo-reductive. That's nice. And finally, if T in G is a maximal K-torus, well, its centralizer will generally not be itself, unlike the reductive case, but at least the centralizer, these are the Cartan subgroups, is always commutative. Okay? And let me just say, roughly speaking, the idea is that at least for 1, 3, and 4, 2 requires a bit more work. But the idea in all of these is what you do is, the idea is you kind of use the magic lemma to infer properties from the maximal reductive quotient over the algebraic closure. And of course, using the hypothesis of the group is pseudo-reductive. Okay? So anyway, this is a kind of list of some sort of nice properties. And I should say that, in fact, one can really go much, much further with this. So I'll just use the reference as CGP, appendix C215, that there's actually a theory of relative root systems and relative root groups for pseudo-reductive groups G over any field, but it has some very different features from the reductive case, namely that the dimensions of these root groups can be very, very large, even when even when the field is separately closed. Okay, so the point is that there is no SL2 crutch. So in the theory of reductive groups, everything gets off the ground in the traditional development, at least, by building off the fact that you know rank 1 groups in terms of SL2. Okay, but in the pseudo-reductive case, there's nothing like that. All right, so in fact, one has to use completely different principles. So one has to use totally different methods to develop this. It's not a matter of pulling things up in the case of SL2, but of course, you also use the known theory for the maximal pseudo-reductive quotient via the magic lemma. Okay, so it doesn't develop the reductive theory anew. You have to use the known reductive theory in the geometric case. But in any event, the point is it really is a kind of good theory of these kinds of things. Okay, so there's a way to kind of dig your hands into these groups in a way that one does with reductive groups using root groups and all the combinatorial information coming from the theory of root systems. Okay, so that's some kind of good news that we have in hand. All right, and so now I'd like to give you, so I haven't really given you a large class of examples. I just said that if you restrict a reductive group through a field extension, you get something pseudo-reductive. But I want to give you a much, much larger class of examples. And so this is what we're going to call the standard construction. And I mentioned at the beginning that Borel and Titz had kind of tried to explore this concept. Actually, this was back in the late 1970s, but they didn't get very far with it. And the main thing, if you had to identify, like, what is it that they were really missing? What they were missing was this. Okay, this what I'm about to tell you. This construction, which gives you a lot of insight into the nature of these groups, is something that they did not have. Okay, so to describe this standard construction, I need to now say something proper about Weil restriction of scalars. So suppose I give you a finite extension of fields, let's say of degree D, and I give you X prime, which would be an affine K prime scheme. Finite time. So you could think about it as like a smooth connected affine group, but actually you'd also, other interesting examples might be things like mu p. Okay, so I definitely don't want to assume that it's smooth. Okay, so infinitesimal group schemes are also quite interesting. And then starting from such information, you make what you call the Weil restriction of scalars, which I'll call X. So the Weil restriction, K prime to K of X prime. And informally, what this is X prime described over K using a K basis of K prime. Okay, and that's not a real definition, that's just an informal idea. And again, you can think about the familiar, I mean, this, in the case of a separable field extension, this is a kind of very familiar operation, and it's analogous to viewing a complex manifold as a real manifold of twice the dimension by writing every complex number in terms of its real and imaginary parts, using the basis 1, I of C over R. But in this general field extension case where things may be inseparable, this will turn out to have some very disorienting properties relative to experience in a separable case. But first, let me tell you the real definition. So as a functor, X of A is X prime of K prime tensor A. So for K algebras. Okay. This is a functor of points, and it represents this. And so just as a kind of basic example, if we take the Weil restriction, K prime K of some affine n space, remember this is a degree D field extension, then it's not hard to see that you get an affine, this is over K prime, then you get an affine space of D times the dimension nd over K. Just like the complex to real case, everything goes up by twice the dimension. Okay, it's also the case that one can show by an infinitesimal argument that this Weil restriction does preserve smoothness, so it carries things that are smooth to smooth, and it also preserves geometric connectedness, which is very useful for groups, in the smooth case. Okay, this is very, very important. You can make examples of things that are geometrically integral and not smooth, for which an inseparable Weil restriction is actually disconnected with a totally non-reduced component. Okay, but in the smooth case, geometric connectedness is preserved. That's been very important when we apply this to smooth connected groups. And of course, in the smooth case, the Weil restriction multiplies the dimension by D, just like we see here in the case of affine space. But let me give another example just to illustrate some of the weird things that can happen. So suppose K prime is K adjoined the Pth root of A, so a degree P purely inseparable field extension in characteristic P. And let's think about the Weil restriction of mu P. So mu P is given by Pth power of the variable is equal to 1, but if you write things over K prime in terms of a basis over K coming from powers of this A, then the defining equation is given by, well, you take a to the 1 over p x1 plus a to the p minus 1 over p xp minus 1 raised to the p power and equals 1. So that's the same thing as the equation x naught to the p plus a x1 to the p plus a to the p minus 1 xp minus 1 to the p equals And the interesting thing is, this is an irreducible hypersurface, not geometrically irreducible, but this is an irreducible hypersurface of dimension p-1, and it's the inseparable Weyl restriction of something infinitesimal. So something of dimension 0 gets promoted to something of dimension p-1 when you do this kind of inseparable extension. So that's a little bit surprising, but this has some consequences. If you take maps like GM to GM by the p-power map, or SLP to PGLP, the central isogeny, these are surjective maps of groups over K prime. But when you apply the Weyl restriction to these things, to these maps, these are no longer surjective. And the reason is their kernels are mu p, which becomes positive dimensional. So when you apply Weyl restriction, you lose some dimension from there, and so therefore the dimension is not enough to fill out the target. Okay? So inseparable Weyl restriction can have some slightly disorienting properties, but at least in the smooth case, things are not so bad. Okay? Smooth goes to smooth, the dimension behaves exactly in the way that it does, given by the case of affine space. Okay, so now I can finally tell you the construction. So we're going to feed in the following information. So we have our K prime over K, which is some field extension. The inseparable case is the most interesting case for what we're about to do. But anyway, just some field extension, which is finite degree. And G prime will be a connected reductive K prime group. And T prime inside of G prime will be a maximal K prime torus. Okay. Now we're going to give ourselves one other piece of information, which is, well, we apply this Weyl restriction functor to the quotient isogeny, sorry, to the central quotient from T prime to T prime mod the center of G prime. Okay, so you've just applied Weyl restriction to that quotient map. Remember, as I said, in general, the inseparable Weyl restriction will not take surjections to surjections. So this map will typically not be surjective when the center here is not smooth. Okay, so in any event, and what we assume that we're given is a factorization of this map through some auxiliary commutative pseudo-reductive group. Okay, I'm not assuming this is surjective. I just have a fact, like C could equal this, C could equal that, or C could be something in between. And finally, this here, well, the group mod its center acts on itself, acts on G prime. And so the subgroup, T prime mod the center, acts on G prime, and therefore its Weyl restriction by functoriality acts on the Weyl restriction, G prime. Okay? So this C here, through this map, acts on here. And so then we can form this semi-direct product. And then we're going to take the quotient by the Weyl restriction of T prime, and this maps in by itself and using this map V here. But we put in an inversion. By putting in this inversion, this turns out to be a central subgroup. So this is a central quotient. And we call this G. Okay? Now, just to give an analogy before we say what properties, this is just a construction. Before I tell you its properties, let me just mention an analog, which is, so we ordinarily think of PGLN as an isogenous quotient of SLN. But what we can do instead is take SLN and take the diagonal of its central quotient acting on itself, and then embed the diagonal of SLN into this using T inverse. Okay, so this is a presentation of PGLN from SLN by using just smooth groups rather than the mu-n as one usually does. So this is a kind of generalization of this way of presenting an adjoint group in terms of its simply connected cover using just smooth connected groups. Okay, anyway, so here's the theorem. The theorem is that this kind of, even though I told you in general, quotients of pseudo-reductive, even central quotients, can fail to be pseudo-reductive. This particular construction, precisely because this C here is pseudo-reductive, this turns out to always be pseudo-reductive. So G is in fact pseudo-reductive. And the map from C to G, which one can easily see has trivial kernel, this is a Cartan K subgroup. I should have mentioned, excuse me, in general, Weil restriction takes Cartan subgroups to Cartan subgroups. So this is actually a Cartan subgroup of that. And so loosely speaking, what this construction is doing is it's fattening up this group by sticking in this auxiliary thing, and it kind of replaces this Cartan subgroup with this mysterious C as a Cartan subgroup. Okay? And so we call this the standard construction. So we call this the kind of standard construction. Well, strictly speaking, there's a generalization. You can make a generalization where K prime, instead of being a single field, it can be a product of several fields. And G prime, instead of being a reductive group over a field, it can be a reductive group over such a product of fields. So G prime here would be a bunch of groups, Gi prime, reductive, connected reductive, over each of those factor fields. Okay? So that's what we'll call a standard pseudo-reductive group, just the output of this construction, right? And one can show that indeed, in fact, in this output, not only is this C a Cartan subgroup, but actually for the output G, every Cartan K subgroup can be realized in terms of the same construction using the same K prime G prime, but a different choice of the T prime. Okay, so perhaps I should make one comment about this before I tell you what can be done with it. So first of all, so for such standard G, there's a kind of canonical choice for the K prime and the G prime. So you can make different choices of K prime, G prime that give you the same output. But given the output, there's a particular kind of minimalist choice, which is actually quite nice for doing Galois descent purposes. And the other thing I should emphasize is it's the form of the standard construction. So it's the kind of shape of the standard construction. That makes it useful to implement this principle. So at the beginning of this talk, I mentioned a kind of general principle that we want to use pseudo-reductive groups to reduce general problems to the commutative case over K and the reductive case over finite extensions. And that's exactly what the standard construction often allows you to do in various ways. But of course, for that to be meaningful, you need to know something about how ubiquitous is the standard construction. And so this is going to be the first main theorem. So to end, I'll tell you some nice theorems. So theorem 1, and this is really the kind of main theorem of the CGP book, which is if P is not 2 or 3, then all pseudo-reductive groups are standard. And when P is 2 or 3, so it's also okay if P is 2 or 3, provided the root system of the maximal semi-simple quotient over K bar has no multiplicity P edges in its diagram, right? So if you look at the diagram of the root system of the maximal quotient, right, it's going to be one of these kinds of diagrams. But for example, types B and C in characteristic 2, right, as well as, well, you can't see it here. Here we go, right? G2, for example, in characteristic 3. So, right, these are problematic, all right? So as long as you're not in those situations, you're automatically standard, and you can really do a lot with that. So that's kind of fantastic. On the other hand, so this is the kind of main theorem in the CGP book. On the other hand, there is a salvage when P is 2 or 3. So I'll just say that for P equals 2 and 3, one can define the sort of generalized standard construction and show it accounts for all but some, I'll just say some zoo for p equals 2. Okay, so so the point is that you can make other constructions based on, well, in characteristics 2 and 3, there are these exceptional isogenies. So for types B, C, and F4, and for type G2 and characteristic 3, there are these factorizations of the Frobenius. And you can use those to kind of make a modification of the standard construction to make more pseudo-reductive groups. And then you can show, and then other things involving like really nasty quadratic forms in characteristic 2. And so you can use that, and this is basically what's done in this book here. And then you can use that to make a generalized standard construction, and it accounts for many other possibilities, okay? But there's still a whole other zoo of examples, and those are also discussed in the orange book, okay? So there's a kind of reasonable, and so certainly for work over local and global function fields, this zoo does not occur. And so one really has a kind of very complete understanding of all the possibilities. So that's really nice. Okay, so there's a kind of tangible way to describe everything, although I'll just briefly comment in passing while I'm erasing here, that in characteristic 2, there's something kind of horrifying that happens, which is there's also a class of groups which have a split maximal torus, but whose root system is actually non-reduced, so type BCN. Okay, and those, we don't have a kind of hands-on construction. We can only make them by using birational group law constructions. Okay, so there's a sort of nastier possibility in characteristic 2, which is quite disorienting, but has some reasonable features, so you can still push through arithmetic applications. So that's great. Okay, next. Here in 3, and this is in the orange book in section 4.1, so this is very nice, which is, although the central quotients cannot fail to be pseudo-reductive, it turns out that the quotient by the full center is always pseudo-reductive, has trivial center, although it can fail to be perfect, might not be its own derived group. And, this is the good news, it's always generalized standard. Okay, so that's fantastic, all right? So if you're trying to prove some general problem or analyze some general structural question, which is kind of not harmed by passing to the maximal central quotient, then in fact, you can always put yourself into this situation that tends to involve groups, which you can sort of describe in a reasonable way, even in characteristics 2 and 3. Okay, and let me just say that by using this, one can actually prove let me just say, a kind of tip style classification. And what I mean by that, excuse me, what I mean by that is the following. So inside G, your pseudo-reductive group, you pick a maximal split torus. You set M to be its centralizer, and M bar to be the derived group of M mod its center. So you might regard this as a kind of anisotropic kernel. And it turns out that if you take the Vinken diagram of M bar over Ks, this naturally embeds in the Vinken diagram for G over Ks. And there's a natural action, it's called a star action on this diagram, on the absolute diagram, just like there is in the case of reductive groups. This is naturally a Galois equivariant subset of this. And it turns out that if you take the group over Ks, this anisotropic kernel over K, and this Galois equivariant inclusion, that this determines G up to isomorphism. And so that's proved by a kind of somewhat more conceptual variant of the argument of Titz and Selbach in the case of reductive groups. So that's very nice. But then, of course, this raises the question of, but wait, what can you say about this in the sense that is there always a kind of split form? Meaning, does G admit a Galois twisted form that has a split maximal torus? Okay, and that can be analyzed, and it turns out that that can always fail over every imperfect field, but the way in which it fails can be kind of well understood away from characteristic 2. Okay, and the same thing with a kind of analog of what would you say? Like you have unique quasi-split inner form in the case of reductive groups, and these also have an analog here. But once again, in the case of characteristic 2, there's all kinds of crazy stuff that can happen. Okay, so if you look in the appendices to this book, there's all a bunch of kind of wacky pathologies in characteristic 2. But the point is that you always have a Tit-style classification, and as long as you're careful about some field theoretic invariance, you even have reasonable analogs of split forms, pseudo quasi-split forms, except that in characteristic 2, things go really crazy. Okay, so I'll stop.